Okay, ladies and gentlemen, welcome back. We are in the final part of what is lesson 4. This was a very long setup. This next part, uh, the first one, part 1 of 2, was just a lot of definition and kind of showing you how this stuff works. It would have been a lot better if we could do this hands-on, but we couldn't, so I tried to do as much as I could running running simulations online. And so I hope that you're able to kind of appreciate a little bit about what's going on. In that, I mentioned a lot about when going from what they told us in the book to going online, that I had to, I couldn't use this thing. I had to change it to this value, and I couldn't do that. I had to change it to this value. And where did those numbers come from? That's what this lesson is about. And this is the primary, this is one of the primary focuses. Like, I do want you to be able to recognize the different symbols for resistance, capacitors, and some things like that. But ultimately, the crux comes in here. Can you use Ohm's law? And there's all kinds of problems that I could put out here that are just fascinating, but I do promise I am going to try and keep them simple and not anything too complex, with just maybe having like 1 or 2 more challenging problems, and we'll see kind of where those come from here in a moment. So where are we going to see Ohm's law the most? It really comes into troubleshooting. Okay. Multiple times when I followed the schematics in the lesson, I used what they said to use. I ran across either I was either like blowing light bulbs because I was generating too much power, or I was not getting enough power, and there would be no light, or the devices would not work at all. So I had to troubleshoot. I had to look in and see, okay, what's going on, and figure out what to do. So it's that troubleshooting process where, for the most part, with the exception of working with the capacitor, I stuck pretty exclusively to Ohm's law, which is voltage equals current times resistance. I've seen it written before in this triangle, because if you are trying to solve for either current, which is I, or resistance, R, then what you end up with is voltage divided by either the I or the R. So like solving for resistance, you get R equals V divided by I. If you're solving for current, you get I equals V divided by R. And if you're solving for voltage, you get V equals I times R. That's how these how these equations work. And you can see that I have them labeled here. If you are comfortable with manipulating equations, you really only need the one, but if you need to, feel free to write down all 3. So real quick, just to recap, what are these things? Voltage is the electrical force that moves the electrons through a conductor. So voltage is kind of like pressure. It's what's pushing everything through. Voltage is the electrical pressure that pushes the electrons. Current is the quantity or the flow rate of the electrons moving past the point. It's not the voltage that really does the damage. It's how fast all of that. It's how fast all of that is moving. Go back to the river example. You can swim very comfortably in incredibly large bodies of water and never have an issue. It's when that water is moving really fast that you run into problems. So current flow, also known as amperage or amps. So we measure current flow in amperage, which I just tend to say amps. And again, that is how quickly the electrons are moving. Resistance is the force that reduces or stops the flow of electrons and opposes voltage. So resistance. I like to think, I've used the analogy of that it's a dam. I kind of like to think of a beaver dam, because unless it's really, really large, it doesn't completely stop the flow of electrons. It just greatly slows them down. And so, there's still going to be some current spillover unless you have a very low current and a very, very, very high resistance. Okay, so now let's just take a look at some examples here. using Ohm's law, determine the missing value for the following circuit. So we have a 4.5 volt battery and 0.5 amps. So what does the resistance have to be in order to create this amperage? The thing about it is that the amperage down here is the same amperage at the other end of the system. So what we're looking for is resistance. Resistance is going to be V divided by I. So it's voltage divided by current, 0.5 divided by, or sorry, 4.5 divided by 0.5. And you get that this was a 9 ohm resistor. As long as current is in amps and voltage is in volts, you don't have to do any conversion. Now, if you run into milliamps or mega amps or megavolts or you know those kind of values, then you do need to do some conversions to go back to ohms. Same thing with ohms, pico ohms or kilo ohms. You know, you have to do the conversions. All right, using Ohm's law, determining the missing value. Determine the missing values. Current, 0.5 amps. Resistance is 10 ohms. So we're looking in this case for the voltage. We're looking at this. You know, I already mentioned current stays the same throughout the circuit, and there are some things you can do to change amperage, but you know we're not getting into that. And so then to find the voltage, it's just your current times your resistance, 0.5 amps times 10 ohms, you get 5 volts. Okay. But now what happens if you start combining resistors? If resistors are in series, which the thing to remember about a series circuit is this is a little bit more my generation and prior than your generation, but you know the infamous Christmas lights strings, where if one bulb went out, all of the light bulbs go out. Okay, that's because that was in a series circuit. What that means is that if there is a disconnect anywhere, then the current stops, because it's kind of like I grew up where there was only one road to my house. There was only one way. There was only one way to go. If something happened to that road, we couldn't go anywhere until it was fixed. At least not in a car. We could walk, but it was half an hour drive to get into town. So you know, walking didn't do us a lot of good. Okay, that's series. When I think of series circuit, I think of these old country roads where it's one road that just goes on forever and ever. And then there's the opposing, which is parallel, which I tend to think of city streets, and I'll talk about that again in just a little bit. The total resistance in a series is just you add up the individual resistances. Okay, so in this case, and as long as you have 2 or more, this always works. So if there were 4 resistors, you would add up all 4. If there were 10 resistors, you would add up all 10. But so for this particular circuit, if I wanted to know what was the total resistance, I would add up, there's a 3K, a 1K, and a 2.5K. So then I would add all of those together, so you get 6.5K or 6.5 thousand, which is 6,500 ohms. All right, calculate the total resistance in this circuit. So now notice here, there's no K, there's no M, there's no micro symbol or anything like that. These are just straight up ohms. I want to know what is the total resistance here. So this is 3. This is a series circuit. There's only one way to go. There's only one path. 3 plus 10 plus 5. And so then that's going to give you a total of 18. 3 ohms plus 10 ohms plus 5 ohms is 18 ohms. Okay, now we want to know what is the current. We know that the total ohms. This is more of the challenge. This is more of the challenge problem. You wouldn't be given this part necessarily, and then you were told to calculate the total current. So you would have to find the total resistance. Once you find that total resistance, you're trying to find current, which is voltage divided by resistance. So you get 9 divided by 18, you get 0.5 amps, or half of an amp. Calculate the voltage drop for each resistor in the series circuit. Okay, so you have 0.5 amps that go through the entire series here. It goes through the entire circuit. And so you want to look at what happens to this amperage as it goes across each of these resistors. So the voltage over resistor 1, that is half an amp times 3 ohms, so that's 1.5 volts. The voltage for resistor 2, that's what the voltage of resistor 2, voltage drop of resistor 2, half an amp times 10 ohms, that's this one here, which is 5 volts. And then finally for resistor 3, you have a half an amp times 5 ohms, or 2.5 volts. And if you add all of these together, what you actually get here is 9 volts. So this is a that would be a series circuit that has a total, a perfect volts. The amount of voltage being produced by the battery is also what is also equal to the total resistance. The total voltage across the system here. Okay. Notice that it doesn't matter which resistor you're talking about. The amperage is the same, and the resistance of each one is based on the resistor itself. Parallel circuit. These are city streets. Voltage through 2 or more resistors are the same, so the voltage stays the same. But then, the current is connected in parallel. The total resistance of the collection is divided among the 3 resistors. So when I think of parallel circuits, I think of city streets. You know, you're driving down the road, and then you see that your pathway is blocked, so all you have to do is go down the next one. And if that one's blocked, all you have to do is go down the next one. Even though all of these have resistors, there is going to be a certain amount of current that makes it through each of these resistors. Okay, and unless it just becomes too much. So again, you know, you can think of a river where even if you give the river 3 paths and you put obstacles in front of it to help slow down the water is still going to split and go down those 3 paths. And so that's some of what happens here. Now this is where the equation gets a little strange. It's similar to the resistors, and again, if it was just 2 resistors, you would just drop this R3. If it was 4 resistors, you would add in a 1 over R4. But when you look at this, okay, I still see resistance. There's R1 plus R2 plus R3. It's just the thing is that they are all now under 1. So it's 1 over R, 1 over the total resistance, equals 1 over the resistance of the first, plus 1 over the resistance of the second resistor, plus 1 over the resistance of the third resistor, etc., etc., etc. So here's a parallel circuit. How do you know that they're parallel? Well, because you can move through any, you know, there is choice for where the current can go. We want to calculate the total resistance of this parallel circuit. So you have 14.4 amps. But all I want to know right now is what's the total resistance. So I have a 10 ohm resistor, a 2 ohm resistor, and a 1 ohm resistor. So I want to know what is the total resistance. So 1 over R equals 1 over R1 plus 1 over R2 plus 1 over R3. R1, the first resistor, is 10 ohms, so it becomes 1 over 10. Plus R2 is 2 ohms, so it becomes 1 over 2. And R3 is 1 ohm, so it's 1 over 1. Okay, do the calculations on this, and you get that 1 over R. Big thing to remember is that this is also 1 over the resistance. Okay, it's really easy. It's really easy to make that mistake. So 1 over 10 is 0.1, 1 half is 0.5, and 1 is just 1. Add these together, you get 1.6. I know that there's going to be, there's a very good chance that I'm going to get that as my answer from a lot of you, because you forget that this is 1 over R. All you have to do then to convert this is just take 1 and divide it by the number you get here. So this is just 1 divided by 1.6. You get that R is 0.625, which is 5/8 of an ohm. Okay, so then that is the total resistance. Find the total voltage across this circuit. So voltage is just the amperage times the resistance, and when you multiply those across, you get 14.4 times 0.625 is 9 volts. Okay, now we want to calculate the current across each resistor in the parallel circuit. So remember, voltage is the same. You have to go back up. Let me go, where was it? Okay, right here, voltage is the same across a parallel circuit. All right, so across the first resistor, 9 volts. 9 volts divided by 10 ohms, that is an amperage of 0.19. Across 2, it's 9 volts divided by 2, so that's 4.5 amps. So 4.5 amps is going to go across this one. And then across resistor 3, you're going to get 9 amps. That goes through that. And that should actually make sense. If you think of water flow once again. So I've got 14 amps here, 14.4 amps, which 0.9, 4.5, and 9 relate to 14.4. I'll let you think about that one for a minute. If 14.4 amps is going through here, and there's a lot of resistance, there's not going to be a lot of current that goes through here. There's significantly less resistance in this pathway, the middle pathway, so there's going to be a lot more current. There should be a lot more current that goes across this resistor than this much heavier resistor. And then this the right resistor has half as much resistance as the middle one, and so it should make sense that twice as much current goes across this one, and which the one resistor was a 9, the middle resistor was 4.5, which is half of this current, and 4.5 divided by 5, because this is 5 times larger than 2, is 0.9. So all of those numbers work out, and if you add them all together, look at what you get. But you get that total current. You get that total current from the original problem. Okay, lots of different areas that we can go with this. Just be mindful, be ready, be able to recognize series circuit, and be able to recognize a series circuit and a parallel circuit, be able to calculate resistance, be able to calculate current or voltage given any of the other two values.